Welcome to our Landin seminar, the FACS group. It's nice to see everyone here. Sorry we can't be in person. It would be much nicer to be having this at the BCS office in London, where we'd be having wine and something to eat afterwards, but sadly we can't do that this time. But we will resume that in the future as soon as we can. My name's Jonathan Bowen, for anyone who doesn't know me, so I'm the chair of the FACS group. And we've just had our AGM, and we're going to continue in much the same vein as last year, certainly with online meetings, but going hybrid whenever we can next year. Anyway, it's a great pleasure to welcome Glyn Winskill as our speaker. This is our highlight event of the year. Glyn was originally read mathematics at Cambridge, so that's a good foundation for formal methods, then also read mathematical logic at Oxford, but then also went on to do a PhD at Edinburgh in computer science. So he's got a very good mathematical background to his computing career that's happened following. He was a Royal Society postdoctoral fellow, and he worked with Dana Scott, who's well known in the formal methods field at Carnegie Mellon. Then he left Pittsburgh in 1984 and became a lecturer at Cambridge University, becoming reader, but then moving to Aarhus in Denmark for a while as a professor. Eventually in 2000 moving back as a professor at the University of Cambridge and working there. He's written the book Formal Semantics of Programming Languages in 1993, so it's still well worth reading. I think it's fairly much a classic of its in its area, and it's been translated into lots of languages as well as English. So now, more recently, he's retired, but of course he seems to be busier than ever. So he's currently based in Scotland at Edinburgh, where he's part of the Huawei Research Centre as chief scientist, but also a part-time professor at Strathclyde in Scotland and still in Copenhagen in Denmark. So he seems to be, like I am, in quotes, retirement, busier than ever after you've retired. I mean, he's worked in lots of areas like domain theory, denotational semantics, concurrent computation, and so on. And today he's going to tell us about making concurrency functional. So I look forward to hearing what you've got to say, Glyn. Over to you.
Thank you very much, Jonathan. And it's an honor to be giving this Landin seminar. As you'll see shortly, I met Peter only once, but it made an impression and a positive one. I'll say something more about that soon. So making concurrency functional. So this is about a bridge between two principal paradigms of computation. The functional one and the less well-established one of interactive computation, where you think of computation as processes interacting with each other. And historically, of course, the functional approach has been very important. It's even the foundations of our subject, where we really, through the Church-Turing thesis, are equating abilities to compute through the input-output behavior. But when it comes to trying to tackle interaction, there are some limitations through the fact that the main way of interacting with functions is by composition. So that can mean that sometimes one has to go through quite a lot of gymnastics to cope with interactive computation within the functional paradigm. The interactive paradigm is much less well established. There are various, I think in some ways it's quite unsettled and still unsettled. But what I'll do is I'll adopt a framework that I've been working on for a number of years with other people, which is a kind of alternative to domain theory and traditional domain theory and traditional denotational semantics, where domains and continuous functions are replaced by games and strategies. So the idea is that you'll get a glimpse of it. You'll get the idea is that one will model types, possibly even general constraints as games, and programs and processes as strategies. Okay, so this is about showing how by specializing to particular kinds of games, one pretty automatically gets many of the developments of this functional paradigm, and some of them are listed here. I don't know how to get a better pointer than this, but that's you see where I'm trying to point here. Okay, as I mentioned, I did once meet with Peter. I was considering where to do my PhD. Almost went to Berkeley, almost went to MIT, and then ended up in Edinburgh. But in the process of settling on a place, I had an interview with Peter Landin, and what remains in my mind, and that was for a PhD place at Queen Mary College London in '77, a long time ago. What remains in my mind is the friendly informality with which it was conducted. I was invited to the student cafe. He bought me a coffee. At that time I smoked, he did too. Lots of Goguens were kind of passed in my direction over the course of the interview, very informal interview. And I remember a few things about it. One was he was explaining what kind of researcher he was. And I remember him describing himself as a researcher like Christopher Strachey, approaching problems in the same kind of way. And I guess I mentioned I was interested in concurrency. So he talked about an approach that he would take, which was to concurrency, which was based on thinking about extents of variables, lifetimes of variables under the execution of a program, thinking about their temporal overlap and dependence. I can't do justice to that idea properly, but I think it ties in a little bit with what I'll come to shortly. Well, as I said, I ended up going to Edinburgh, but I got this, I wish I'd kept it, this in an envelope. I got this corner of a computer printout with "Glyn, are you still interested, Peter?" scrawled, I think, in green ink or something. And anyhow, but so that was really, unfortunately, the last contact I really had with Peter, though I think I heard him talk once in Edinburgh, but that was just at a general talk. Okay, interaction via functions, and this will have something to do with those ideas of Peter's on looking at the extent of variables in programs. So of course, we're all used to functions computing from input to output in this kind of way, and used to the idea that the way we make them interact is by composition. But if we're talking about a more full-blown interaction, then we want to be able to somehow interrupt or affect the computation of this function as it's going on. We want to accept input from the environment. I'll just get rid of some of this. Input from the environment by using a parameterized function, which is allowing us to take some information from the environment along the course of the computation. So we're using some kind of product-like construction, possibly product, possibly something a little bit more general. One can take account of the fact that there might be more going on than just computing from A to B. We may be taking input, and we may be interacting with the environment by taking input. But if we can take, oh no, it's happening now. But if we can take an input, why can't we give out output as well to the environment? And if we do that, then of course we can start joining little functional units together in this kind of way. But why should all of the output to the output interaction from F go solely till G? Why couldn't it go to some other process in the environment of F? More this kind of thing here. Why can't some of the output go to some other potential process in the environment? So we end up with maybe a functional unit looking something like this, showing the kind of interaction with the environment you might have. And if we add in, as is popular these days, back propagation to do learning, then we end up with another arrow going back to give us feedback in order to update our parameters and make maybe the calculation of the function better. So we have a fairly broad scheme with which to describe functional computation. But of course, what I've said hides a lot. It hides the nature of the functions. Generally, we need enrichments to functions which are, for example, partial, if we want to cope with the fact that computation might diverge. Given that we can introduce loops in the way I was connecting functions, we might want them to be continuous, so we can talk about fixed points. And we might even want to go outside traditional functions and think of what were often in the old days called many value functions, and allow functions to be non-deterministic, where they don't give a unique result for a particular input. But here there's a warning. It's known since the work of Brock and Ackerman in the early 80s that if we try and give a compositional semantics to non-deterministic data flow of the kind that we could support if we had non-determinism and looping, then we have to go outside traditional input-output relations. We have to look at a more intentional model. So it's not entirely clear what kind of F this should be. There's another issue too, which relates to that talk of extent that Peter and I had all those years ago, which is that functions and their usual input-output types can only give a rather static partial picture of the dynamics of interaction, which can be very rich. And dependent types can help, but I would argue that we need a way to describe and orchestrate the temporal pattern of interaction, fine-grained dependencies there are, and possibly dynamic linkage that occurs between functions. Why should they be just hooked up once and for all in a certain way? And this is not a mile away from what Peter was thinking about. What Peter Landin was thinking about, if you realize that these lines here are really variables. And so one is talking about activation of these lines in the same way, I think, that Peter was thinking about activation of variables. But how are we going to describe and orchestrate the temporal pattern of interaction and its fine-grained dependencies and dynamic linkage? Well, use a model that copes directly with dependence. And this brings me on to event structures, and I've just explained the simplest kind of event structures in this talk. So event structures are designed to talk about the dependence of actions. So an event structure consists of a set of events, really event occurrences. They don't repeat. And they're partially ordered by a causal dependency relation. So when you see something like this, it means that in order for E to occur, it needs the prior occurrence of E prime. And we'll assume that the causal predecessors of an event forms a finite set. And then because we want non-determinism as well, we have a conflict relation where written in this way, which we'll take as being propagated upwards through causal dependency. If two events causally depend on conflicting events, those two events are themselves in conflict. So in this model, we can also talk about causal independence or concurrency of events, namely when they're neither in conflict nor causally related. So here's a little example, little diagram of a typical event structure. The boxes are the events. The causal dependency, immediate causal dependency, is represented by these arrows here, and the conflict by this wiggly line here. So this event on the right is in conflict with this event on the right. If one occurs, then on the left. If this one event occurs, it excludes the other. This event here causally depends on both of these two events. In order to occur, it needs both of these two events to occur. So if this event occurs, it blocks the occurrence of this, and this event cannot occur. In the manner in which I've indicated, there is an ensuing notion of history or state associated with an event structure, namely a configuration, which is intuitively is the set of events that have occurred up to some stage in a computation. So you'd expect that subset of events to be consistent. No two events within the set should be in the conflict relation. And moreover, if an event has occurred, all of the things on which it causally depends should have occurred as well. So that gives us a notion of configuration. And if we gather together all the configurations into a set and we order them by inclusion, we've got something that really is a very special kind of Scott domain, familiar from denotational semantics, where more information corresponds to more events occurring. To give you an idea of the power of event structures and tie in with work later, let's think about trees as event structures. Here's a simple process. You might think of it as a game, but this might then be the decision the decision tree associated with playing a game. There might be two initial moves that can be made. One excludes the other by this conflict relation. And then when this move has been made, then subsequent moves are possible, which might be in conflict with each other and so on. So if you think about what the configurations are here, they're either the empty set or some branch of this tree, some branch of events. Now that might be a game. We might imagine putting two games in parallel. So we would have maybe a green game and a red game like this. And if it were just to stick with trees, this wouldn't be a tree. We'd have to do something to make it a tree. But as an event structure, we just lay them side by side, and that gives us an event structure. That is an event structure. We might imagine that this event here on the left, this green event, represents the win of some particular player. This represents the win of some other particular player. And we might use that then to spawn off some other game in this kind of way here. So we'd start the new game here, and then the ensuing game is given in this kind of way. So this gives you an idea of trees as event structures, and moreover, how event structures are much more expressive in what they can say than trees. Now, what I want to do is take these event structures and make them into a model for interacting processes. And the idea for this, I first met in a talk of John Conway. Pretty sure this was when I just started in Cambridge and went along to an Archimedeans meeting where John Conway was talking about numbers and games. And I didn't realize how important, as you often don't when you're a student, I didn't realize how important the idea was. The idea is subsequently being kind of refined by André Joël. So they both deserve credit, I think, for expressing and exposing this idea, which deserves to be wider known than it is. It's a way of turning two-party games into a model of interacting processes. It's based on several ideas, the key ideas I'm giving you here. First of all, we're thinking of just two-party games where we have player versus an opponent, but we think of that dichotomy as really being that of process versus the environment being all those things over which we have no control. Once we have such two-party games, we'll assume, and for the games we're considering, that they have two operations on them. One, that one can form the dual game, where you just interchange the role of player and opponent. So when I think of strategies in such a game, I will implicitly think of the strategies as being strategies for player. So I can get a strategy for opponent, a counter strategy, by thinking of a strategy for player in the dual game. So the role of the dual game is to reverse player and opponent. Comes in a lot in the constructions we'll see. Then we'll assume that we have a simple parallel composition of games. Just imagine there might be two games of chess that you play in parallel, that kind of thing. The importance of these operations is that they give rise to the idea that we can talk not just about a strategy in a game, but a strategy from a game to another game. So a strategy from a game G to another game H, and we're thinking about strategy for player here, is going to be a strategy for player in the compound game given by taking the dual game G and putting it in parallel with H. The importance of this is it gives us an idea of composing strategies. Imagine we had another strategy from a game H to a game K, namely a strategy in this compound game here, the dual game of H in parallel with K. Now notice that a strategy in the first strategy, when player thinks they're when player is making a move in H, that is a player move for him, of course, but it's regarded in the other strategy as an opponent move and vice versa. So we have, informally speaking, a way of composing these two strategies by letting them play against each other in the common game H. So we have a notion of composing strategies. which has turned out to be an incredibly fruitful notion. It's the foundations of game semantics and allows the kinds of reductions that Conway was talking about in his numbers and games, where less than or equal to on numbers is actually realized by a reduction on games. Okay, once we have this notion of composition, turns out that generally there's an identity, and that identity is given by a kind of copycat strategy. So given a game, the identity should go from game G, the identity should go from G to G, so copycat should be a strategy in the dual game of G parallel with G. So let's look at an example. You've probably seen this before, but let's imagine that the game is the game of chess, where we distinguish the player as playing black. So that's the game of chess. Then it's the dual game would be the same game of chess, but where we reverse the role of player and opponent, so player is now playing white. And then the strategy going from chess to chess should be a strategy in this compound game given by this parallel composition here. So imagine you're a player. How do you play this strategy? Well, you could be a very naive, this is well known, I guess, you've probably seen it before, but a very naive chess player. And the way you can play the strategy is by essentially waiting for the white player on the right to make a move. Then you copy it over as your move on the left. Then you await a move of the black player on the left, the opponent on the left, and then you play that on the right, and so on and so on. And in this way, despite being a simple-minded chess player, then you could possibly win against a grandmaster. So now we're going to take those ideas and turn them into a model for distributed games and distributed strategies. So it's really, the slogan is we're using Conway-Joyal on event structures. As I've indicated, you often think of a game in terms of the decision tree, the different moves that are made. But here we're replacing that idea of tree by an event structure. But we need to distinguish what kind of moves the events correspond to. So we're going to label the events by a polarity, a plus or a minus, according to whether they're moves of player or opponent. And for technical reasons that I won't probably mention ever again in this talk, is I'm going to assume that the game is race-free, in that we have no immediate conflict, immediate's important, immediate conflict between player and opponent events. Whenever player and opponent events are in conflict with each other, that's always due to events on which they depend of being in conflict and then being either both player events or both opponent events. Well, once we've got this view of games as event structures with polarity, there's an obvious operation of dual, namely just switch the polarities. And as you've seen with trees, we can do simple parallel compositions with event structures just by juxtaposing them and not introducing any extra conflict. So we have a parallel composition as well. So once we've got a notion of a strategy in a game, we have a strategy from a game to another game in this way that Conway and Joyal told us. And I'll write such a thing in this way. But of course, it begs the question, what is a strategy in a game? Well, roughly, a strategy for player, remember, should be a choice of moves for player together with their causal dependencies on opponent moves. So if we go to Copycat, if we imagine an event structure game A, it could look like this here. It may have lots of causal connections and lots of conflict. I've not drawn any conflicts here. I've just drawn one causal connection. What this is saying, this part of the game is saying, you wait for this move of opponent, and then when opponent makes this move, then player can make this move. The dual game would be the same structure, but with a reversal of polarity in this kind of way here. So what's the copycat strategy from A to A? Well, following the spirit of Copycat, player should just await what opponent does and then copy it. And that we can do by just adding causal links in this kind of way. We just, for any player move, either here or here, say, in one game or the other, what we do is we look at the corresponding opponent move for this one here, for this one here, and we put in extra causal links. And doing that, once we tidy up a little bit with conflict relation, does give us an event structure, which we can think of as representing the Copycat strategy. And if we thought of that original Copycat strategy on the games of chess, and we represented each game of chess by some kind of decision tree, then this would give us the appropriate Copycat strategy between them. Unfortunately, when we come to general strategies, we can't just always just take the game and add in extra causal dependencies. Things can go wrong if we do that. So we have to move to something a little bit more general. We have to think of a strategy as being given by an event structure itself, which is really standing for the choices of moves that a player makes, together with how they depend on the opponent moves. And because these are meant to be moves in the original game, we have a kind of labeling function, which is pinning those moves to moves in the original game. Now, if you think of a configuration of S, that's to be thought of as a state of play, where you are with respect to a state of play according to this particular strategy. Then you'd like that configuration under direct image of this function to go to a configuration of the game, which you would then think of as a position of the game. But you don't want to be able to make more moves in the strategy than are allowed in the game. So you expect some kind of local injectivity condition like this. If you have this original state of play X, if you have two events, two moves in it, if they go to the same move in the game, then they have to be the same. So here's a little example of such a strategy expressed in this kind of way. The game is a simple one, but it's a concurrent game. It consists of two opponent moves concurrent with a player move. And imagine we have a strategy where we want to answer any move of opponent by the player move and not answer prematurely. We don't want to make a move unless opponent really has made a move. So this is how we might do it. We could make the move, the player move, if we see the left-hand side opponent move, or we can make the player move if we see the right-hand side player move. And then if the opponent plays either one or the other move, then if it just plays the left move, then we do this event. If it played the right move, we do this event here, we make this move here. But if opponent happened to make both moves, which is quite conceivable, then we would non-deterministically choose whether to make the move according to it being justified by the left player move, left opponent move, or the right opponent move. So I hope that gives you an idea. There'll be another slide in a moment to give you more of an idea. But if we do that, this is a reasonable strategy. But there are things that these maps would allow that wouldn't be reasonable. We don't want in our strategy to be able to enforce constraints on the opponent which are beyond those given by the game. So in particular, if we imagine a state of play and its corresponding position in the game, we don't want, if the game says that the opponent can make a move from that position, then we better make, in the game, then we better be able to make that opponent move in the state of play. And moreover, you don't want to make any additional causal dependencies beyond those of the form player awaits moves of opponent. It wouldn't be fair in this game, for example, if in this strategy, for example, if we said, make this opponent event here await this player move here. That doesn't seem at all right in the spirit of a distributed strategy. So the only thing we can do is make in a strategy is in this S part of the strategy, it can have additional causal constraints which were not there in the game, but the only causal constraints are such that they're associated with immediate causal dependencies where player awaits moves of opponent. I'm hiding. Oh, sorry, I'll just now, this idea of representing a strategy as a function in this way might be a bit non-standard. I mean, you would often, if you were given a game represented by this decision tree here, you would often describe a strategy for player by describing at each node the choice of action that the choice of move that they would make. So for example, you might say, at this way, opponent makes a move, and then player decides to move to this right, make this right-hand side move, and then maybe decides to make the left-hand side move. Well, that kind of thing is coped with in this framework as well through this kind of map here. You see that this map is telling you you're going this way. I'm hiding a lot of the mathematics underlying this from you, but I want to give you an idea about it. So we're concerned with, if we're composing two strategies, one going from A to B and one going from B to C, then we do that by essentially synchronizing their complementary moves over the common game B. In the same way that if one's used to, say, CCS or CSP, in the same way as one does synchronizations there. And then, of course, one's left with synchronizations over this common game that you want to hide. So there's some technology that needs to be used to do that. And in fact, to do this synchronization, one uses a construction called pullbacks, which is a construction that's very useful when you want to join behaviors together associated with some two processes with some common interface. Anyhow, once you've got all this method in place, you can then prove a theorem that those conditions of receptivity and innocence on the strategy are precisely those which are needed to make copycat identity with respect to composition. In other words, if you take one of those maps and you just, if you like, don't impose any constraints on it, and you compose it with copycat, you'll only get the same map strategy back again, or same map back again, if that map satisfied receptivity and innocence. So this gives us a rationale for the correct definition of strategy in this extended framework, where we're no longer working with trees or sequences, where we're working with partial orders. And what one's got then is a notion of distributed game given by event structures and distributed strategy or concurrent strategy between these distributed or concurrent games. And they compose, and one has identities and so on. So one has a rich structure there. And there's lots I could say there, but one of the early surprises was that French domain theory came out as a very special case. So there's this stable domain theory invented originally by Gérard Berry in 78, based on things called DI domains and stable functions. And we'll get exactly that for a certain kind of game. But first of all, I need to, the strategies you will have to look to connect up with stable functions have to be deterministic. So let me just tell you when a concurrent or distributed strategy is deterministic. It's deterministic when conflicting behavior of player is always due to conflicting behavior of opponent. In other words, player doesn't introduce any conflict. Okay, and now let's look at some particularly stupid games. Games A and B, which are purely player games. Opponent doesn't even get a look in. All the moves are those of player. Now let's think about what a strategy is from such a game A to such a game B. Well, it's going to be a strategy in this compound game here, comprising dual game of A, where now all of the moves have become moves of opponent. In parallel with B, where all the moves are moves of player. So think about causal connections in S. Think about events in S. There might be, if an event, if an event is a player event, it has to go to the right-hand side. If if a move is an opponent move, it has to go to the left. And remember those restrictions on strategies. The only extra causal dependencies you can introduce are ones where player awaits moves of opponent. And moreover, because of receptivity, you can't put any restrictions on the opponent moves. So what you get is that, so in such a strategy, you have player moves, which, if you like, can become activated or triggered when certain opponent moves have happened. And if we look at deterministic strategies where player can't introduce any non-determinism, then I think it's not too far to hope that you can see that that's going to give you some kind of function. And in fact, it does. It gives you exactly the stable functions that Berry introduced on his stable domains. And in fact, the configurations that one gets, the domains you got from these configurations of event structures, are his DI domains. So one has reproduced his domain theory here just by choosing some particularly stupid kinds of games where opponent doesn't even get a look in. Now, this is a game theory. This is a domain theory, I meant to say. This is a domain theory. So it does have a function space, and it's Cartesian closed, so-called, and it has a product and so on. I won't go into what these stable functions are. They're special kinds of Scott continuous functions, and here's the description of what they satisfy. This domain theory of Gerard Berry got rediscovered and reinvented by Jean-Yves Girard in his coherent spaces in a rather restricted situation. Coherent spaces correspond to event structures with trivial causal dependency, namely identity relations of causal dependency. And that's been very, very important, of course, as it was the foundation for his discovery of linear logic, which has been really has had a tremendous effect on semantics of programming languages. Okay, what about staying with these stupid games, but looking at all strategies, possibly non-deterministic? This time the same holds, that the only causal connections can be from left to right, making a player move causally dependent on opponent moves. But this time we don't need to restrict to deterministic strategies. So several player moves can occur here, and they might be in conflict with each other. What we get now is something that's called a stable span. And what this is roughly is for each player move, it tells you what outputs it's associated with and what it needs in order to be triggered. In other words, what finite configuration it needs in A in order to be triggered. These are roughly kind of non-deterministic stable functions. They also, given any configurations that are related in A and B, where given A, you can get that, given a configuration X in A, you can get configuration Y in B out, it's telling you maybe different configurations which can give rise to it. So it's giving you a kind of relation, but where instead of just saying something is in the relation or not, it's giving you a set of ways of realizing the way that pair can be in the relation. So in fact, one's also got a way of looking at these stable spans as special kinds of profunctors. Now, they're not as well known as stable functions, but they have been central and been discovered and rediscovered several times, principally in providing a compositional model for non-deterministic data flow. So we're on the right track. Remember, if we were going to use function-like things, we were broad enough to support non-deterministic data flow, then we would have to move outside a traditional input-output model. And we're on the right track with these stable spans. Let's make the games just a little bit more complicated. This will tie up with Girard's geometry of interaction, which was a way of exploring the nature of proofs as networks. Roughly, the idea is that you think of, as we all know, sometimes in a proof, bits can be proved independently of other bits. You could have several people working on a proof independently and then joining their results together. And in fact, that's what mathematics is. It's like trying to get some big strategy for a proof. It's often not just one person doing the proof. Okay, so it's perhaps not surprising then that one recovers geometry of interaction by looking at special kinds of games. And these are just one step more complicated than the games we've just described. Let's now consider a GOI game, a geometry of interaction game, to just be a purely player game, A1, in parallel with a purely opponent game, A2. Okay, and let's imagine that we're interested in a strategy going from A of one of these games to B. So here they are. Now, remember that the events of B1 are all going to be player events. The events of B2 are all opponent events. And because when we take the dual of this, we'll get reversal, we're going to get an opponent event associated with A1 and a player event associated with A2. Now think about what causal dependencies you can put on here. They can only be from these opponent events to these player events. So you can have causal connections like this, going from left to right, or going from bottom to top, or for this event, from this guy to here, or from this guy to here. So what one's got this time is that a strategy, a deterministic strategy at least, corresponds to a pair of stable functions. One going from this to here, and one going from this to here. In other words, these two stable functions here, which we can represent in this kind of way. Now imagine that we had, so a strategy looks like this, and in fact the composition coincides with a strategy, with the composition that you might think of. Imagine joining two such pairs of functions together. What you can see is happening is you're getting a loop here. So if you want to give this composition, you have to use least fixed points, which are supported by these stable functions. And what one recovers by doing the composition is Abramsky and Jagodishin's GOI construction, which they originally did for Scott domains, but now, and as they recognize, this can equally well be done for stable domain theory based on DI domains. More generally, if we look at applications of geometry of interactions, it's been very useful in understanding optimal reduction in the lambda calculus, and more recently in token machines, where you implement languages in terms of graphs of tokens moving along them. And when tokens move along edges in the graph, they move forward or backwards. And that's what this splitting up into the left and right, associated with the two different polarities, that's what is associated with this moving in both directions across an arc of a graph. The player events associated with player moves are associated with emitting a token, and the opponent moves are associated with accepting a token. Now, to get further connections, I need to look at extensions on these games. They've been extended in various ways, and in particular, they've been extended with winning conditions and imperfect information. So I'll just briefly tell you how one does that. So a winning condition on one of these games, represented by an event structure, is just specifies those configurations which are a win for player. And a strategy in such a game is winning for player if any maximal play for player results in a winning configuration of A. Now, subject, of course, to the fact that opponent has made certain moves and not others. So given that given that player moves depend on the opponent moves, that can vary according to what the maximal play is, will depend on what the opponent has done. And then it turns out that a strategy from a game A to a game B is winning if in any maximal play for player, a win in A implies a win in B. And winning strategies compose by virtue of this implication being associated with the conditions, the winning conditions. For imperfect information, what we can do here is imagine that not all moves can be dependent on all other moves because they might not be able to see those moves. So we have we imagine a kind of access order on moves of the game. And we insist that you can only have a causal dependency in the game or in the strategy if it's allowed by the access order. And such strategies, when restricted according to this imperfect information given by the access order, also compose. And that was a bit quick, but let's look at a particular example, a very simple example that turns out to tie up with Gödel's dialectical interpretation. So a dialectical game is a GOI game, one of those games that we saw earlier, just a purely player game in parallel with a purely opponent game, with winning conditions, which is going to specify pairs of configurations from the first part and the second part, which are regarded as winning, but subject to imperfect information in the sense that one has access levels 1 below 2. So you think of these as two rooms, room 1 and room 2, separated by a wall, but where there's a one-way mirror, so that opponent who's in room 2 can see moves of player in room 1, but not vice versa. Then we think about what a deterministic strategy between such dialectical games is. We have a restriction on the strategies associated with GOI games, because now we have a player move in B1 could previously depend on an opponent move in A1 and in an opponent move in B2, but now the dependency on the opponent move in B2 is forbidden by the access order. 2 can depend on 1, but not 1 on 2. So what we get is a restricted kind of restricted kind of strategy associated with these dialectical games, namely to something that's called a lens in functional programming. And remember, we had winning conditions as well. What winning means in this case is a funny kind of backwards condition written in this kind of way. But this is exactly the backwards condition that Gödel wrote down in his translation, in his dialectical interpretation, where he was associating assertions in his system T about higher order functions with assertions of arithmetic. So here, deterministic strategies coincide with between dialectical games coincide with Gödel's dialectical interpretation of proofs in arithmetic as higher order functions. There are lots of applications of these ideas. In particular, one can, because of this interpretation of Gödel, of understanding assertions in arithmetic as in terms of higher order functions, it gives one the chance to do proof mining, extracting algorithmic information from proofs. And a great deal was made of that by George Kreisel and Ulrich Kohlenbach, and much more recently by Ulrich Kohlenbach. We can look at when Valeria de Paiva wrote her thesis, she met Girard, and he suggested an alternative to the access order that we've just seen. The access order we've just seen allowed a kind of one-way signaling where opponent in room 2 could see player in room 1, but not the other way around. But what we could imagine is just forbidding just putting a solid wall in between the two rooms. And then in that way, we can enforce non-signaling. And then if we look at deterministic strategies with respect to such games, which satisfy this, and strategies which satisfy this non-signaling condition, we get very special kinds of strategies where we just have pairs of maps going in opposite directions in this kind of way. Of course, these ideas of signaling and non-signaling appear in physics. And indeed, the combs of quantum architecture, and these arise because people were trying to look at high level ways of understanding their string diagrams or quantum circuits. These arise by another kind of generalization or extension of dialectica, of the access order with associated with dialectica games. Namely, we just imagine extending it to having n rooms, which are separated by these one-way mirrors in the way I've described. And imagine that we have, instead of just having two games of different polarities, we have games of alternating polarity in this kind of way. And then we see for such games that a strategy between such games is what's called a comb. And I've drawn the reason why it's called a comb, because it has these teeth here. And if we looked at just dialectical games, they'd be associated with just this part here. So this would be the F part, and this would be the G part, which depends both on this, on B2, and also on A1. But it's a way of rearranging the maps so that we can see ways to compose things. This is asking for having another comb put in here, or which might be a single tooth. And so in this way, one puts some kind of discipline on those otherwise unstructured string diagrams or quantum circuits, and gives some higher order view of how to combine those quantum computations. What about general, possibly non-deterministic strategies between dialectica games? These correspond to optics, which have been discovered and introduced within functional programming. And what an optic is a way of combining maps. So here we have a map. It happens to be so the strategies correspond to optics built out of stable spans. One stable span is going from A1 to B1, and then an auxiliary thing called a residue, which is then used by G. And in this way, one couples together the two maps, the one associated with F, the one associated with G, and they're coupled together. And when we do this kind of construction, we get precisely, when you're producing this kind of construction, we get precisely the strategies between, the general strategies between dialectica games. By virtue of the fact that stable spans have a function space, we can actually simplify and describe an optic just as having this type, as a stable span having this type, where the Q here has been replaced by a function space. Let's look at some other stupid games. Containers are data structures where you have shapes which index positions, and those positions can be filled in various ways. So you might have a shape 5 or something, and that can be associated with lists of where they have associated with lists which can take 5 items. They arise from container games, which we get in the following way. We've previously assumed that the game split into two parallel components, one associated with player and one associated with opponent. Let's not do that now. Let's just imagine that we have a game which is such that a game which has to respect access levels 1 below 2, where each player move is assigned 1 and each opponent move is assigned 2. Well, if you think about it, then the only causal dependencies in such a game are concerning moves of different polarities are the ones where opponent is dependent on player. And so what this game A looks like is lots of player events, lots of player moves, followed by opponent moves that may depend on them. So what that means is a configuration of A has the form of can be decomposed into a union of a player part and an opponent part. And so what that means is a container game corresponds to a dependent type of this kind. first do the player part. Dependent on the player part, you can then do some opponent part. Okay, so a container game corresponds to a dependent type. And in fact, and of course, that dependent type, you can read it in the context of containers as this X as being a shape and the A2X as being the positions associated with that shape. When we look at what deterministic strategies are between such container games, they correspond to something that's known in the literature as a dependent lens. This time, the function going backwards depends on the particular player moves that have been made. So we have a dependent type here, which can be expressed, and we can express such a pair as itself having a dependent type, either in this way or less standardly this way here. Well, what about looking at container games? What about looking at general, possibly non-deterministic strategies between container games? And for the first time, we begin to get something that might be new. I don't know if it is. We get something that I'm calling dependent optics. Certainly the name has been used before. And what they are things of, well, if we go back to that previous slide, they look very like what we had previously as a characterization of the type of strategies between container games. I'm probably running out of time, but if one then here's the composition of such dependent optics of this kind. It's defined in rather informally in this kind of way, using some let notation. But I think if you think about how you would compose such things, I think you come up with the idea here. Okay, so for a variety of rather simple-minded games, we've recovered several functional paradigms. Those different paradigms often are accompanied by different problems, like how does one add probability to them? How does one add quantum effects to them, and so on? How does one make them work with real numbers if one's trying to turn those paradigms into something for machine learning, for example? Well, games and strategies support such enrichments to probabilistic strategies, also with continuous distributions, to quantum strategies, and also to extensions, enrichments with smooth functions to support differentiation. And these have been tested by getting full abstraction results with respect to program equivalences and so on. And all of these things were done fairly, one inspired the other sometimes, but they were done as independent pieces of work. We've had the recent realization that all of these enrichments can be achieved in a uniform way by the same construction. Using, and harking back now to the third slide, using parameterized functions. The idea is that we want to have very general functions, so we'll have a symmetric monoidal category. So this is just functions of an abstract kind that can support some kind of product. So for example, we might have a simple monoid, the monoid of the reals in the unit interval with multiplication. For that particular instance, that's the thing that we use to get probabilistic strategies. Or we might have something much more complicated, namely completely positive maps, where the objects are finite dimensional Hilbert spaces, and then the completely positive maps act between them, saying how states are transformed from one Hilbert space to another. That would be the appropriate place to do quantum. That is the appropriate place in which to do quantum strategies. So once we have such a general class of functions supporting some kind of product, we can assign moves of the game to objects in this category. Okay, in the case of this first example, the assignment will be just to the, everything will be assigned the unit interval, quite boring. In this case here, completely positive maps, the assignment would be of a finite dimensional Hilbert space to each move. Then for the strategies, to make the strategies probabilistic or quantum or whatever, the uniform method proceeds as follows. We look at an interval between two configurations. So we imagine a configuration growing from X to X prime. So within it, there will be, and this is within some strategy. So the events will be moves of player or moves of opponent. What we do is we assign parameterized maps over M to such an interval. So roughly what we do is we look at X and X prime, we have these events in between, and we use the polarity and the position of the events with respect to its dependency to orchestrate the functional dependency and dynamic linkage that's needed in composing such enriched games and strategies. Of course, this is only giving you a flavor of how it goes. It's quite complicated, but that original idea of Peter Landin of looking at extents and wondering how one might control and understand those different extents is having is echoed here in this orchestration of the way that one links together parameterized functions. So in conclusion, the functional approach is the one we know and love and I feel comfortable with, and it can help tame the wild world of concurrent interaction through providing simpler models. But those simpler models have been, as you can see from the names associated with them, these are geniuses basically. They were not so easy to discover. And in particular, it gets even harder when you want to look at those models, lenses, optics, or whatever, and enrich them in some way with probability or quantum structure or real number computation. So here, this is where distributed games and strategies can provide a broad general context for interaction, which specializes to functional paradigms and moreover provides through this specialization, provides enrichments to those functional paradigms to probabilistic quantum and real number computation, etc. So it might be hard to work with these distributed games and strategies. There are technical obstacles and difficulties, but in some ways you do things there and you've got a whole load of things that come for free. And moreover, sometimes one gets things that are not being done elsewhere. Okay, thank you very much. That's me done.
Thank you very much, Glyn. That was a wonderful talk, very, very well presented. And I was really enjoying your new number theory on the slide numbering.
Oh, sorry about that.
That's okay. Once you started going over 22, I was wondering where we were going to go. Don't worry. I was enjoying seeing the numbers moving about. So thank you very much, Glyn. I don't know if it's best to unshare the screen because then we can sort of see each other, and anyone who wants to wave. The easiest way to ask a question is to either wave or just unmute yourself. So does anyone have any questions?
Yes, I think I have a question. Hello there. Hi.
Hello, Brian. Nice to hear you.
Yes.
See you. Hello.
Long time. Yes, indeed. This has been a fascinating talk, absolutely fascinating, and quite new to me. I have bumped into your lectures on event structures and monoidal categories and so on a little bit, but the intuition has been a little bit hard to grasp, to be honest. I would like, yes, I would like, if you can, perhaps to give us a bit more of a flavor of how one might use these kinds of ideas as motivations for maybe operational semantics that would be then applied in a context. I realize that directly applying this is probably not quite the flavor of what you might want to do, but you might use it to justify other technologies and techniques that would then be tangibly applied in, say, a concurrency situation.
Mm.
I wonder if
Yes,
you could...
well, if we look at the GOI games, for example, people tend to look at GOI for deterministic and non-concurrent scenarios.
Yes.
This generalizes, I mean, at least in principle, generalizes that context to allow several tokens to flow around concurrently. So one has potentially here, I mean, one has a semantic, one's proceeding kind of from the semantics to the language maybe, or the implementation, but one has the potential to do that here by giving an operational reading to what's going, how the events are changing, because a trace of events would correspond to movement of a token through the system, for example, and one could then try to read from that. Well, in fact, there already are ideas on how one might generalize these GOI machines to handle concurrency. So one can look at those and start giving them a semantics and see. But there's much more to it than that, because GOI is just one way of doing things. The strategies come along with an operational semantics. We got that worked out way back in some 2014, I think.
Right.
So one has a meta language and an operational semantics in which, at the cost of not hiding when you do composition, one has a correspondence between the derivations in the operational semantics and the events. So one can start using this to push back into operational. One has a language, and one can start using that language, and that language is useful in contexts that one might not think of. We can talk about if there's somewhat, this is incomplete, but just as winning strategies compose, one can show that in some contexts that optimal strategies compose, and one has a language then for talking about optimal strategies and building up optimal strategies in a compositional way. There's work to be done there. There's lots of gaps in that work, but there are certainly some initial results there showing that can be done. So I think this feeds into more operational concerns, but I'm probably not the best person to do it, and that's why I didn't want to retire. I wanted to team up with people, and the people in Huawei are working on some things that are related to this, and certainly so I'm hoping for interactions myself with them and with other people to come out of this work. But you're right, there is an overhead here. Mention pullbacks, and some people just get turned off immediately. So it's not always so straightforward to get followers.
Thank you so much. Thank you.
Thank you. Any other questions from anyone? Do either wave your hands, switch on your video, or just unmute yourself and ask. I can only see half the screen at the moment, so I might miss you if you don't do that. I mean, you mentioned Huawei, Glyn, so now you're involved with Huawei. Are they, what sort of formal things are they doing? How related are they doing things to what you're doing? And
I think I've got to be careful what I say.
Oh yes, okay, fair enough. Fair enough. Well, whatever you're allowed to say.
There are relations, yes.
Yes.
Yeah, that's right, yeah. Because I think it's no secret that they're setting up Dan Geek has been very successful in building up a research group there, and there's still capacity for more people to come as well. And my role there is still being defined, I think, to some extent.
Right. Okay. Well, good luck with this. A new career, I guess.
Yeah, I know.
Yeah, yes. Yes. Yeah. Okay. Any other questions? I can scroll my screen to see if I can spot anyone. Or Brian, do you have any more questions? Because Brian is going to write a report on this talk, so that's why he's probably interested in writing. Now is the time to ask, Brian, if you're not sure of anything that Glyn has said.
I think I've seen quite a lot of your publications. Are you planning on as it were, making a broader publication for a wider dissemination out of the notes and so on.
Yeah, yes.
Very, very interesting indeed. I think there's plenty of scope for that.
Yes, I'd like very much to do that. You know, if I'd stayed in Cambridge, I think that's what I would have done. I would have started writing a book about event structures and games and so on. But that didn't work out. So that's what I would like to do now, I think. But I think the first thing I would do is I've written, because I was involved with the CRC project and writing, I'd often would go up, forge ahead and get things worked out before giving them to other people. There are lots of exim notes to do with that project, which I would try and get published in some. They're a bit messy at the moment. I'm trying to tidy them up a bit and get them published. Now, they're rather technical. They're not very accessible. Some bits of them are, bits of them aren't. So that's the first thing to do. And then the next thing is then think about writing a book. And it'd be nice then to be involved with some teaching. Because event structures have not caught on in the way that I think they should have done. They're used, I know, in weak memory models, but they're used in a rather, for one exception I know of, work of Simon Castellan, they're used in a rather elementary kind of way. Whereas Simon, he does use the power of product in order to cope with different ways that one might different weak memory assumptions that you might impose. He systematizes that using the product, but otherwise I think people have tended not to use any of the categorical structure, which is essential, absolutely essential here in getting this this to work.
Very interesting indeed. Yes, thank you.
Thank you. Any other questions from anyone?
I think it was Margaret who's just put a hand up.
Oh, Margaret, there you are. Do unmute yourself, Margaret. You're muted at the moment.
A very foolish question, probably, but you spoke of this as being related to learning systems. Now, learning collects, as it were, instances to work on. So I'm not sure how the collection works out. This is a very sort of basic question, really.
Yeah. Well, I was meaning, there are certain people who formalize in functional languages how one can do learning algorithms. So people like Spivak and then there's open games of Jules Hedges and so on. And there, what one's concerned with is having a function going in one direction, which is approximating the thing that you want, and then you do some gradient descent, which is a function going, which gives you, by reverse differentiation, a function going in the opposite direction and tells you how to correct some of the parameters in that function. So what you do is you have some hypothetical, you have some approximation of what you're trying to get. Then you compare it with some measurement and you find you're away from it. So you use gradient descent in order to try and improve the parameter, tweak the parameters to get the right function.
It's iterative, isn't it? Iterative.
Yes, it's iterative.
Iterative, the way there's sort of some numerical mathematics works, isn't it? In an iterative fashion.
That's right. Yeah.
Yes, I wasn't really thinking about that so much.
No, I know. I know you were thinking of. I mean, yeah, that was what I was. That when I mentioned learning, that's what I was thinking of, because they're certainly concerned with how to wire up functions in non-standard ways, and they use these things like lenses and optics to do it. But I think in terms of your more general view of learning as being assembling data, that you can do probability here, so you can do Bayesian inference in that way by conditioning in various ways. Now, whether that conditioning can be pushed to the level of strategies, I don't know, but that would be nice to do. You know, because I can model first order things and second order things, and I can do some of the stuff there. That should be fairly routine, but it would be very interesting when one could maybe get some purchase and get something new would be if one wanted to talk about learning strategies.
I was thinking more about inductive learning, which is the way scientists work, isn't it? They induce generalization from set instances, and that which, or they correct a particular concept using a collection of instances, some of which, you know, diverge away from the original concept, and then they use induction to correct the original concept, or even to create a new concept, that which is the way scientists work, isn't it? Obviously, yes.
Yes, yeah.
I was thinking more of that kind of learning, but I mean, obviously, everything can't be useful for everything. So that is an example of the kind of learning where this perhaps would not be appropriate. Is that right?
Well, I think lots of people are thinking about these more general kinds of learning in the context of, once you start making things abstract, it's not so much what work I've done here, but once you start making things abstract, as in kind of these open learners and so on, then there are different ways you might instantiate so you can have different analogues of gradient descent. It doesn't necessarily have to be directly related to real numbers and so on. So there's work of people like Fabio Zanassi and people that does that kind of thing. They're looking at Boolean, or actually, can I remember? Better not say too much. I'm not really good at getting it to getting the ideas to forward in
yes.
Time.
Yeah. See what I mean? Well, there isn't usually. I mean, the kind of learning I'm thinking of, it's more sort of directed learning. It's not kind of, you know, it's universal, and you can just throw everything in and then say, come on, let's turn the handle and it spews out. You've got to point. It's human intervention to say, oh, it's look, we'll have a look at this aspect. Look at that aspect. So it'll probably be different variables you would look at if you're thinking about your iterative manner.
Yeah, but if you were to formalize that, you presumably have some metric.
Yes.
Which would then guide you as to how, you know, you're then, with respect to that metric, you try and minimize something. Or
I was thinking about this kind of thing we did with air traffic control, and we formalized. We had a look. It was where there was the concept was of the safe space between aircraft flying across the Atlantic, and the metric there we had a look at. We focused on was there were all kinds of variables. Was it, as you correctly say, a metric of intervals that we looked at? So that there was a metric there, in fact. Yes. Though we didn't look at anything else apart from metric, so I don't know anything about anything else. Yeah. Okay. Sorry.
No, it's fine. No, thank you. That's interesting.
Thank you. Any other comments? I think I can't see anything in the chat at the moment, but anyone want to unmute yourself if you've got something you'd like to say?
Someone called Annie. Annie?
Oh, right. Oh, Annie. Yes. Well, do go ahead, Annie.
Okay, I was wondering if there are any playable games, like entertainment kind of games that are using this notion of gaming or making it learnable to people.
No, not that I know of. I think this is still aimed at, really, initially it was aimed at semantics of programming languages. Now it's become a little bit more general than that, but it's not really close to the gaming industry, I don't think.
Not logically close?
Well, possibly logically close, in the sense that one could possibly understand some of these games, describe some of these games as distributed games. The kind of problem I'd have would be that you'd have to discretize things. You know, your games are going on with, you know, in space somehow. So you'd have to talk about moves between different positions and that kind of thing. And I don't know how one would do that.
I was just thinking of the way you described optics as maps. So games usually have maps. They're overlapping maps in this.
Well, I don't know. I've not thought much about it, to be honest, so I don't really know. So I can't really answer satisfactorily, I don't think.
That's okay.
Mm.
There was something that you said that I was wondering if you could provide an example or just sort of demonstrate. You said if I think you said this, if two events coincide in a conflicting, like, composite event,
Mm-hmm.
then those events are themselves in conflict.
Yeah, in some ways it's not quite what I said, but what I think I said was, but it's not wrong what you say either. But it's that if you have two, so you're right with them. One of these functions only be going from S to A, that I talked about, which the strategies are based on. That would be the case, that if two events in S went to the same event, they'd either have to be equal or in conflict with each other. That's right. But what I did say was that if you looked at a configuration which was like a state corresponding to a state of play, that would tell you what moves you made, and you better not make any more moves there than were allowed by the game. So what that meant was if you couldn't have two moves in the state of play two distinct moves in the state of play going to the same move in the game. It would be like a game of chess where somehow in the strategy you move the knight twice, whereas you're not allowed to according to the game. It would just not be allowed to do that. I don't know if that makes sense.
What was somebody about to say? I was just going to say that Ian Stark has also got a question or his hand up. So you're muted, Ian.
Okay.
Yeah.
Hello, Ian.
I should be now. Hi, Glenn. Oh, I enjoyed the talk very much. That was lovely. And it's really nice to have you back here in Scotland. Although limitations on movement at the moment are a bit strange.
I know. Are you okay? You're sounding a bit...
Sorry, I have a cough, actually. So I was interested, I mean, you've related these polarized event structures to a whole range of different kind of distributed and concurrent settings for interactive computation. I'm interested in hooking this to a more kind of process algebra forward presentation, which of course has the same interaction happening, but is a different way of presenting how you structure your computational processes. And what's the mapping like between, or the representational model for having event structures to represent varieties of process algebra, or in particular things like join calculus as well, where you have multiple interactions going on?
We've not gone that far in that direction. There have been student projects where people have modeled CCS in this situation. There's a reason why I'm not that keen on it. It's because I think there was a wrong choice made with process algebra a long time ago. And that was a symmetry in the synchronization of events. You know, if you think about CCS, the A's and the A bars, there wasn't much difference. Just one happened to have a bar on, that was all. Whereas the synchronization that occurs in strategies, there's an asymmetry in that, if you like, opponent moves are accepting and player moves are kind of positive. They're giving something. So sorry,
that's the difference between action and reaction.
So that affects the kind of algebra. So if you start looking at May and must equivalents and things like that, you get things are different. There are different equivalencies. And I'm more keen on looking at that. And we have done some work on that. There's a paper that's archived, and it's going to be appearing as a Samson, some Samson-Abramsky test script thing. That's about May and must equivalence on strategies. So treating the strategies as processes, and putting in the thing that I've hidden a little bit here is that strategies, because they can, when they compose, there can be some deadlocks that occur that you won't necessarily see unless there's extra structure around, like probability. Then you'll see it in terms of probability leaks, or you can do it more economically as well. But then or you can just not hide events. That's another thing. So you see these tau-like events,
internal ones,
and then you can see what the may and must. But if you hide things too much, the must and you don't have extra structure like probability to see leaking, to see leaks of probability and something, things like that, then you miss this, and you can't really formalize things properly. So that's the direction that we've gone in. So I think this, and I believe in this asymmetry. I mean, I think that people have raised issues about implementation of CCS because it's apparently not really feasible sometimes to do it. Whereas I think that with this asymmetry between player and opponent, then I think those issues will disappear.
Yeah, so I mean, that's certainly so in the, as you say, classic CCS is entirely symmetric, as is kind of some variants of pi calculus. And then people have indeed identified that what looks completely concurrent and distributed, in fact, is not. You can't. I know Anna Ingolstadt did some work on this. You can't completely distribute things. But some of the refinements of that are to focus on, yes, differentiating between the kind of active and passive, the output and input, that, or you may send an output is active, but you may equally receive or be prepared to receive multiple things. And some variants of Davidis and Jordi had some restricted versions of the pi calculus, and the join calculus as well has some of that asymmetry baked into it. Asymmetry saying, these are not the same kinds of action and reaction, which I think then would also introduce, kind of captures the kind of thing you're saying, that player and opponent are not identical. If you reverse them, then yes, you're swapping the polarities, you're not mashing them all together. Okay, no, that's really helpful.
So I think there's overlap.
I understand that disconnect there.
Yeah, and it's and I think there's work there, and I think there's been successful work in tying up these ideas to session types, for example.
Right. Yeah.
And that begins
strategies
to though I'm, well, you know me, I'm not that keen on fixing on the syntax too early. I'd like the mathematics to suggest that. And I, my view is session types are too much fixed on the syntax.
Right, and these things very much start from the syntax and then try and
that's right.
I can see that.
It's not the way I would like to go, but it's but other people do it and they do it very well.
Okay, thanks very much.
I think Brian's got a follow-up question. So.
Yes, indeed. Yes, I have. You began the talk with mentioning Conway's numbers and games. This is just a quick question about that kind of world. Do you see any further relationships with that kind of work? I don't know if anybody's actively exploring that at all. But
no, it's not being done. It's surprising. As far as initially, I gave it as a student project to an intern, Simon Castellan, and then he was so brilliant that he got involved with our work on symmetry in games, which we needed, and we kind of went on in that direction. But you can model Conway's games and strategies within what we've done here. It's not quite as natural as the things I've shown you, in that you can restrict the games, the tree-like games where you don't have alternation. Winning conditions are all right, but then you have to restrict the strategies in some way. The strategies are alternating despite the games not being. So there's some oddness there, but you can model it. I just don't see what you get from it really so much.
Yes. Okay. That was my next question. Really, was the follow-up of if so, what insights did you obtain from that? And
not really yet, but I mean, it's a pity. There is a kind of student project there still waiting to be done, and I think that understanding what this idea of winning strategies and then a strategy from a game A to a game B, giving you a way of reducing a winning strategy in A to a winning strategy in B. I think that kind of idea seems to me very could be fruitful and should be followed up, I think, in other contexts. I mean, I'm naive about complexity things, but I've done some work in trying to understand some recent work on strategies understood as Goguens maps. And the funny thing there is that the composition of strategy is given by the composition of Goguens maps. Now that seems very odd, But there is a way of reformulating it game theoretically so that you see that composition of co-authorizing maps is actually coinciding with composition of strategies, a la Conway and Joyal. So I think there's kind of there's a general space around there, I think, which is kind of interesting to try to analyze and understand.
The final comment I want to make is that in Conway's book, he was making the point that there are other, the whole thing generalizes vastly. Of course, you obtain effectively a universe of sets and so on. And so, I mean, there's this whole idea of Peter Axel's of what was it? It was the idea that you could have descending chains and so on. You could have entire universes.
Mm-hmm.
So that speaks to a huge generality of this kind of work.
Yes, yes. I've only picked up some bits of it. That's right. I think that's true. I wonder if the finiteness condition on event structures will get in the way sometimes of this.
Yeah, that's so you wouldn't have the non-descending condition.
Yeah.
Quite right.
But where we have had successes is in tying in with proofs and so on, and getting a kind of compositional proof of Herbrand's theorem, this kind of thing, where you understand Cutter's composition of strategies, and the other success has been in quantum strategies. That the published version of quantum strategies is not as general as we'd like it to be. And so that seems to me to be potentially very fruitful, because there are ways of understanding those strategies as Petri nets with some quantum structure on them. And I think that I think would have an effect on, could have an effect, because people would find those things fairly easy to use, and it might mean that people. So in other words, there's a kind of synchronized, there's a process algebra of quantum Petri nets where you can synchronize actions together, so you can get compositional accounts of things like teleportation and so on. Of course, people can do those things with string diagrams, but I think that what we've got is the string diagrams would correspond to configurations, and we've got the extra non-determinism as well on top of that, and maybe more chance of doing higher order quantum things in a more streamlined way. Sorry, I'm going off on a tangent here, but but there's some work on higher order quantum things which has to get stuck, because if they're not careful and don't type things properly, they introduce loops and causality loops which get in the way. All those things are dealt with here in these strategies. When the pullback condition eliminates those causal loops. So I think there's a chance of being able to do some of the higher order quantum architecture stuff more straightforwardly in these quantum strategies. I'm talking too much. That's rather a tangent.
Lynn, thank you so much for that. That was really, really interesting. Thank you.
Thank you. Any final question? Danny, did you still have another?
Well, you were just talking about high order things, and it reminded me that you were saying understanding assertions in arithmetic in terms of high order functions, and what would make that a high order function.
Yeah, it's because, so what Gödel's translation did, it took some first order assertions about arithmetic, and then he was interested in proving consistency of arithmetic. That was really rather a pure thing he was trying to do. So he first of all translated them to Heiting arithmetic, and then he got this dialectica interpretation on top of that. So then there were first order assertions, and he understood, and he eliminated, he could rewrite all of those original assertions in terms of there exists some higher order functional such that for all higher order functionals, an assertion without any quantifiers in it at all. And those assertions without any quantifiers in it at all, they're the things that correspond to the games that we were getting when we did the dialectical interpretation. So he was pushing all the complexity in arithmetic into the complexity of these higher order functions. And you know, we tend to maybe have more faith and belief in those higher order functions than we have, because they give us a, you know, they give us the higher order, they give us a higher order view on things, and maybe a more higher order belief in consistency because of that.
Thank you. And go ahead, Annie, if you wanted to respond.
Oh, I was just saying thank you. And it's if I understand you, maybe the thing that's making the higher order functions more solid seeming, or more less subject to dependencies.
It's more that they're more familiar computing objects. I mean, computable objects. You know, the functions on integers and functions on functions and functions and this kind of thing. That we, you know, we're not, you know, we're used to programming these kinds of things. It was all done within System T, which is a kind of higher order programming language where we restrict to primitive recursion, a kind of generalization of primitive recursion to cope with functions.
Right. Well, unless anyone's got any final comments, I'd just like to say thank you very much, Glyn, because it was a beautifully presented talk, and very nicely connected with Peter Landin, which we always like.